Hi guys, this is video 2-3 to be watched the weekend of Friday, September 30th. And right off the bat, I'll tell you what the homework's going to be after this video. It's going to be from the homework packet, page 5, number 3. So I'll write that here. So the homework will be page 5, number 3. Just one problem. Okay, so today we are going to use the limit definition of the instantaneous rate of change of a function at a point, otherwise known as the derivative, otherwise known as the slope of the tangent line. Okay, so the derivative of a function is the instantaneous rate of change of the function at a point. So in this picture right here, I'm just going to interpret this picture for you. The things that we have going on, we have a secant line. Let's focus on that for a moment. So here's the secant line that's intersecting the graph twice. This point here is C comma FC. And this other point here is C plus H comma F of C plus H. So the x values of these points are a distance of h away from each other. Okay, we just added h to that x value to get over to the other one. Okay, so there's that. Now I'm going to go off to the side real quick, and I'm going to put these 2 points that I circled in pink in a table. So x, y. Okay, so the first point is C comma F of C, and the second point is C plus H, F of C plus H. Okay, so the slope of the secant line, which is the same thing as the average rate of change, that the slope of that line right there, is f of b minus f of a over b minus a, otherwise known as the change in y over the change in x. So I'm going to go down here and I'm going to write the average rate of change. So the slope of the secant line, or the average rate of change, is f of c plus h minus f of c over c plus h minus c. Well guys, c plus h minus c, that's just h. Okay, and if that doesn't make sense to you, then, go off to the side. I'll actually do it anyway. So c plus h minus c, look right there, guys. So that's just h. All right, so change in y over change in x. This is the slope of the secant line. Now, the secant line will give us the average rate of change. We are not interested in the average rate of change right now. We're interested in the instantaneous rate of change. At what rate is this function changing at a certain moment, at a certain single point? And this is a hard problem because we don't have 2 points to, use our regular notion of slope on, change in y over change in x. We've just got this 1 point on the graph, and we're trying to find the instantaneous rate of change at that very point. So what I'm going to do now is I'm going to put a series of points on the graph, getting closer and closer to this point here. And let's suppose that we want to find the instantaneous rate of change at this very point. So what I'm going to do is I'll start with my secant line, and I'll keep this point fixed right here on the graph, but this point that we started at the x value of c plus h, I'll just, I'll move that to one of the points on the graph that's closer to the point that I want the instantaneous rate of change at. Okay, and then I could, move it to an even closer one, and move it to an even closer point, and even closer and even closer. And eventually, guys, if I keep repeating this, my secant line is going to get closer and closer to this tangent line, okay? And the slope of the tangent line is what I'm interested in. That is the instantaneous rate of change. Well, now think about this, guys. Remember, this h is the distance between this x value c and this x value c plus h. H is the difference between them. So as my secant line is becoming my tangent line, think about what's happening to h, the distance between the x-coordinates of my two endpoints on the graph. H is getting closer to, think about it, 0. So guys, if I want to take my average rate of change formula and I want to turn it into an instantaneous rate of change formula, I need to let h go to 0. So in other words, I need to take the limit as h approaches 0. All right, so this right here, guys, this is the instantaneous rate of change. This is the derivative of a function at a certain point. Okay, so down here, the limit definition of the derivative. If I want to know the derivative at a certain point, this is the prime notation for it. So f prime of c, that's the instantaneous rate of change or the derivative at a point c, and it's given by this limit formula. The limit as h goes to 0 of f of c plus h minus f of c over h. And notice, ignore the limit, that's just the average rate of change, but we're letting h go to 0. So the distance between those two endpoints of the secant are going to 0. Yeah, the distance, okay. So now, how are we going to use this formula? Well, usually, guys, instead of c there, we're going to be using x's. So what I would like you to do now is, let's just put an x over those c's. That's how this formula is usually used, with looking like that. Okay, so we're going to do a couple examples, and then you only have one problem for homework. So here's example 1. Use the limit definition of the derivative to differentiate. Differentiate just means find the derivative of the function f of x equals 6 radical x plus 5. Write the derivative in prime notation and Leibniz notation. So I don't know. We'll see at the end if I actually want you to do that. I wrote those directions last year. Okay, so if I'm going to use the limit definition, and those of you who are in physics might know a faster way of doing this, but don't spoil the surprise for everybody else. We're going to do it the long way, which is using the limit definition. Okay, so, oh, there goes my phone. All right, I'm going to ignore that. So I'm going to go like this. I'm going to say to myself, well, I know that f prime of x is equal to, and f prime of x is the derivative, the limit as h goes to 0 of f of x plus h minus f of x over h. All right, so I take the average rate of change, or the slope of the secant line, and as h gets smaller and smaller, as h approaches 0, it gets closer to the tangent line, and the instantaneous rate of change is the slope of the tangent line. Okay, so what I have here is, I'm just going to use the function that I know. This is going to be the limit as h approaches 0. F of x plus h, I'm just putting in x plus h where that x is. So it's going to be 6 radical. So x plus h is going in for x. So x plus h plus 5. Okay, minus 6 radical x plus 5. Okay, so f of x plus h minus f of x over h. Now remember from last unit, our limit techniques. Always try direct substitution first. Can I plug 0 in for h? No, that would make the denominator 0. So this is where, guys, I would take the expression that you're finding, the certain limit of, and I would go off in a margin. Okay, so 6 radical x plus h plus 5 minus 6 radical x plus 5 over h. So I'm off in a margin. I'm going to try to simplify this so that I can actually use direct substitution on it. Notice that there's radicals involved. So the strategy is to multiply by the conjugate over the conjugate. So the conjugate is 6 radical x plus h plus 5 plus 6 radical x plus 5 over itself, x plus h plus 5, radical x plus 5. Okay, and I'm using parentheses. Okay, so difference of two squares there. So this is going to be 36x plus h plus 5. All right, those parentheses are important there because it's going to be 36 times that whole thing. Plus, oh no, minus 36x plus 5 over h times 6 radical x plus h plus 5 plus 6 radical x plus 5. Now guys, I hope at this point you recognize that the thing we want to cancel is the h. That's what was giving us the problem. We couldn't plug 0 in for h because that would have made the denominator 0. So I'm hoping that h cancels. So I'm going to simplify more here. I'm distributing the 36. I just had to turn the light on. So this is 36x plus 36h plus 36 times 5 is 150 plus 30 is 180 minus 36x plus 180 minus 180. Okay, this whole thing over h times 6 radical x plus h plus 5 plus 6 radical x plus 5. Okay, well this looks promising, guys. These 36x's cancel. These 180s cancel. And I am left with 36h over 6 radical x plus h plus 5 plus 6 radical x plus 5. And my bad, the whole thing is, it should be an h out in front of there. And these h's cancel just like I was hoping would happen. So now I'm going to go back up here and I'm going to section this off. Okay, so I'm going to go back up here, and because of this work I did off in the margin, I'm going to make the observation for my reader that the limit as h approaches 0 of this is equal to the limit as h approaches 0 of my simplified expression off to the side. 36 over 6 radical x plus h plus 5 plus 6 radical x plus 5. Now, at this point, can I use direct substitution? Absolutely. Because if I plug 0 in for h, so this h is getting closer and closer and closer to 0. If I make the h 0, it doesn't make the whole denominator 0. So I'm going to go ahead and do that. So at this point, I'll end up with 36 over 6. Remember, h got closer and closer and closer to 0. So this radical approaches x plus 5 plus 6 radical x plus 5. This is equal to 36 over 12. Oh, that's a 5. Over 12 radical x plus 5. All right, I'm going to simplify that a little bit more. Let's just use prime notation at the end. So therefore, I don't know, the 3 dots is a nice presentation. So therefore, f prime of x is equal to, what is that equal to? 3, right? 3 over radical x plus 5. Okay, there it is, guys. This is kind of a long video. Okay, you know what? I'm going to just stop there and have you try the homework yourself, okay? The homework should be it should be easier than what we just did. And then in class tomorrow, if you guys are struggling, we'll do more examples together, okay? So I'm going to stop this video now. The homework is to try your hardest on page 5, number 3. Okay, guys, I'll see you later. Bye-bye.